Hello and welcome everyone to this numerical method project for university. My name is Kevin from Group P12, and in this video I'm going to discuss a code, a simple software, quote unquote, that me and my group has designed for the project for basic heat propagation simulation in two-dimensional reservoirs using the finite difference heat equation method from partial differential equation, and in this case we'll be using it for simulating thermal EOR, or thermal enhanced oil recovery. Um, First of all, I would like to clarify that this code is largely inspired by someone on YouTube, and we will be putting the link to his discussion on the Python code in the description. And the next thing is that keep in mind that to run this code, you need to be using either Visual Code or the Jupyter Notebook and not Google Colab, because it will not work on Google Colab or it will not work properly. So without further ado, let us continue by running the code. And another thing that I would like to clarify is that this code will not work. I mean, it will work, but it will take a very, very long time if you put a very big number on your variables, be it time, length, or nodes. So, for time's sake, we will be simulating a rather small reservoir of 150 feet with a simulation time of, say, 5 hours, and we're going to have around, say, 75 nodes. No, what are nodes? So you have x and y axis, as this is a two-dimensional space simulation with time. So 75 means that each of your x and y axis will be divided into 75 nodes. So yeah, let us continue. And normally in more basic simulations, you're going to have the same bottom boundary temperature from left to right, but in this case it's a little bit more complex, and you may enter two different values for your bottom boundary temperatures from the leftmost to the rightmost. So in this case, we will try 150 to 500 Fahrenheit. Top boundary 150 and 500 Fahrenheit. The same for the left boundary. But for the right boundary, say we will keep it at 68 Fahrenheit. Now, when you press enter, this little window will pop up with the simulation, with the time, and it's going to run the simulation. So this is one of the reason why this code will not work on Google Colab, as this will only show the first iteration and will not continue to the next one. And so we have it here. Simulation finished. I have put a timer for the total running time just in case. Yep, it ran for 37.5 seconds roughly. And if we take a look at this graph here, and if we check 18,000 seconds is roughly equal to 5 hours. So yeah, it's more or less the same as the user input. Of course, there are a very tiny deviation on the time output, but for this simple, for code this simple, I think this is rather good. So let us try with a very big number, because I also want to show the weakness of this code. So say we have a very big reservoir of 50,000 feet, and we want to simulate it for 100 days with a number of node of 75, the same temperature as the previous one, and it diverges very quickly. This is because there are certain threshold on the method used, in this case finite difference on from PDE. There are a certain threshold, and if the threshold are not met, then the code will diverge very quickly. And this is certainly not an accurate representation of the real life condition, nor is it close. So that is the weakness. And once again, I'm going to run with a fairly big number, but it's reasonable. Say we have a reservoir of 250 feet, and we want to simulate it for 24 hours with number of nodes of 50 with the same temperature as before. Still works, but it's going to take a long time. 24 hours is around 86,000. So if you bear with me here, it's going to reach 86,400 very soon, hopefully. But yeah, any second now. Yep, there you go. 86,428 seconds, and it takes us 28 seconds to run. Now it also shows here the average temperature, by the way. If we calculate this, it will equal to 24.007 hours, which is very close to the 24 hours of the user input. And again, for a code this simple, I think this is fairly accurate. Although in real life, probably there will be more aspects that affects heat propagation in reservoirs, but this simple code will provide a simple reservoir heat propagation simulation for two-dimensional reservoirs. It will be an entirely different story for a three-dimensional model. So I think that's it, basically. Oh, and one last thing is that the thermal diffusivity is 0.0445, and this is adjusted in feet squared per second for sandstone. And I'm pretty sure you can find this online on Wikipedia for various materials if you want to try heat propagation or heat diffusivity for copper wiring or anything else. You can find it online in a Wikipedia page. So that's all, and yeah, thank you for watching.